alkenes. I mean, we did alkenes, so now we're in alkynes. Thing to remember about alkynes is that we're dealing with, 2 pi bonds. Right, so you have 2 pi bonds and a sigma bond. Our structure for this, right, we have our sp hybridized, we have our hydrogens that are s, and then we have 2 p orbitals. And if we draw our overlaps, right, we got our overlap there and there, and change our color, and we have the overlap here and here. So our carbons are sp hybridized. They have 2p. What was wrong with the score? Sorry, going back to answer question. There was nothing that was wrong with the scores that had me worried. It was that we had some students that I'm not sure, let's put it this way, either they learned to study for exam 2 and hadn't learned to exam for study 1, or they had a hard time with the adjustment to exam 2. And so what I saw was not that the scores were bad, but I saw people that had big differentials between exam 1 and 2. And so that big differential, I think the best way to take care of that is to do a best 3 out of 4 exams. It shouldn't hurt anybody, and it gives people that either struggle with exam 1 or struggle with exam 2 a chance to recover from that struggle. So there was nothing wrong. In fact, I was quite happy. A lot of you did incredibly well. Even got some of the questions that I thought were more difficult really well. And so, no, I would say the class as a whole is doing excellent, but there are some people that had some big differentials between exam 2. I think the best way to give you all a chance to recover from the change and is just to give you all a little buffer there. Okay, so let's see. So we got SP. So remember, there's some things that are important to remember. That when we look at our SPs here, our P's, right, is that they're orthogonal, right, which means they're isolated. The 2 pi p orbitals, the 2 pi bonds, don't interact at all, so they do not communicate with each other. That means that more or less what I'm dealing with here is 2 independent pi's. So it's not like I have conjugated pi bonds. I have 2 independent bonds, and that's going to be important in the reactions and what we do with this. Okay, so let's start at the beginning. So that's our base structure for what we're dealing here. We're dealing with sp carbons. Okay, let's look at nomenclature. The nomenclature is pretty straightforward. If I could spell nomenclature correctly. We just change our suffix. So now we're going to use "-ine". So if we're naming it as an "-ine", that gets priority. Like before with alkenes, you can put the number next to it. That's really more whenever you get to really complex structures where it might get confusing. 3-hexyne is what you're going to see most often. Hex 3-ene would be shown as a accepted substitution. Where you'll see the number being moved next to the suffix is going to be whenever it gets really complex, lots of different groups attached. When you look at this one, right, we have 1, 2, 3, 4, 5, 6, or we have 1, 2, 3, 4, 5, 6. So we can have 2 and 2, right? But in this case, we're going to put the 2 that goes with the 2 that goes with the suffix, right? So that's our priority. Our suffix is our priority. And so that gets the 2. That means the methyl gets the 5. So remember, when you have side groups, the side group gets a lower number than your your suffix. Again, as the ine here, your ine would need to be 2 and 3, right? So just like with our alkenes, if you ever get a position like this, you need to put them in the first and second position, right? So as we go around those, there are some cyclic alkynes, but as you can understand, with the fact that this is, 180 degrees, you've got to get to really big rings before you can put a 3-membered ring in it and not cause a lot of strain. So there are some cyclic ines, but they usually are very big, 8, 9, 10 cyclics. The other thing on nomenclature to understand, and we'll be using this even today, is that you actually have 2 basic structures. You have internal and you have terminal. And these have different reactivities, specifically acidity. Right. So when we look at a terminal alkyne, we have this group on the end, conjugated as well. The triple bonds are not conjugated. So I'm not sure of your question. So if you want to readdress that, I'll try and answer it. So we have terminal. So internal, right? You have carbon group. Terminal, you have a hydrogen on one end, and that's going to change the reactivity that's going on here. Now, the big change here is the acidity of the terminal alkynes. And if we remember our alkanes, right, our pKa value, right, was about 50, very oh, you can have conjugated triple bonds. If you had triple bonds, single bond, triple bonds, those would be conjugated, but you're not going to have conjugation between the 2 bonds. So yes, if they're separated by a single bond, they can be conjugated. If we look at the pKa's of an alkene, right, this is sp3, this is sp2, about 44. But then when we go to a terminal alkyne, that's sp. Now we have more S nature. That brings that in closer. Now we're getting down to a pKa range of about 25. So 25 is slightly less acidic than, let's say, an ester, the beta hydrogen on an ester, or we can see that the pKa of NH2, right, is, well, NH3, the pKa value is about 35. Right, so we know something in that range, and we are aware that sodium NH2 is not hard to make. In fact, you take ammonia and drop sodium in it and let it sit around for a little while, and you'll get some of this. But so now we have a much more acidic proton, which means that unlike alkanes and alkenes that really do not have acid-base reactions, now if we take a strong enough base, and the amide is our strong base, this is going to pull proton. Oops, that's not what I want to do. And those electrons are going to go back, and we end up okay, questions? So what this means, right, is now that we have that negative, if we bring in something that's less acidic, like water, We can do the proton there, right? So we have to watch for protic solvents, because this is a good base, but it's also, and we'll see this more later in the chapter, it's also a really good nucleophile, right? So now we've converted that carbon to a good nucleophile, and we can add carbons and carbons. We've got carbon bond forming. And of course, this only works for terminals because with internals, we don't have a hydrogen on there. So there's not something to react. So preparation. So remember, if we took an alkyl halide and reacted that with a good base, now if we do the same thing with a dibromide, so we need this is called a geminal dibromide, because both bromines is geminal because both bromines are attached to the same carbon. That refers to the geminal here. Now, if we add a good strong base, and then follow it with water, notice we're doing it in ammonia here, we can end up with the alkyne. If we look at the mechanism, okay, this first subtraction probably could be done with a weaker base like the methoxide to end up giving us but then this next subtraction, again, just drawing the arrow down because I'm running out of room, right? So then that will abstract there. Now I need the really strong base, right? So this is where I need the strong base because that proton and this elimination process is going to need a stronger base than an alkoxide. This first step probably could occur with an alkoxide, but the second cannot, right? So that's why we need this stronger base. That then will change my color back. That then will, oops, and I need to get my angles right. Sorry, guys. And so we get this, right? And we still have the H, but what do we still have in solution? We still have the strong base, right? So we still have the strong base. The strong base is strong enough to deprotonate this. Right? Giving us that, right? So now this is all step one, right? And thanks for not pointing out that I had two steps ones, right? So we got step two. So step one, and then here is step two. Here's where we bring in water, and all the water is doing is reprotonating our alkyne. Our acetylide is what it's called. Okay. Okay, so we can prepare alkynes from dibromides. We can also do that with vicinal dibromides. And again, here.
Dr. Morvant,
Yes,
sorry, just going a little bit quick,
a little bit quick. Okay.
trying to follow along with notes. Yeah, I just want to see that second step real fast and just make sure I get the notes on it real quick.
No problem. So if we have an internal one like this, and it could be geminal or vicinal, but I do want to show you an example of vicinal. In this case, right, I'll end up with a triple, but notice I don't need a second step. The reason you don't need a second step here is because I don't have to worry about this deprotonation of the terminal alkyne. This one is not called, so the question about E2, this is really an E2 process. This one is functionally not called an E2 specifically, but you can think about it as a concerted process. It's not called an E2 because this is an sp2 carbon. But then you have the deprotonation. So yes, your analysis there is very close, okay? And then here, right, we've got just the stop. Once we get the deprotonation, you would just stop at this point, and then you would have no deprotonation because you have no acidic terminal. So internals, you just need the reagent. You need to follow up with water. And again, this is one of those cases where if you understand the process, you'll understand the difference. Okay. Question about preparation. For reduction of alkynes, again, we're dealing with, notice that so far, a lot of these look a lot like the alkenes. And the same is going to occur here with reactions of an alkyne. If we take an alkyne with palladium and hydrogen, we'll actually reduce that all the way to the alkane. Again, what's happening with these is we've got hydrogen absorbed, right? That helps break that hydrogen-hydrogen bond. Then we add our triple bond. The triple bond, right, is absorbed to the metal. That's what I'm trying to signify there, right? And we have our hydrogen, and then that gets that reaction. And then we have this, right? But an alkene can absorb to a surface. And get the same type of thing. So we end up with the alkane. So the question here is, if we had one equivalent, right, what would happen? So if we take a triple bond and we add, let's say that we're really careful and we add one equivalent of hydrogen with palladium on carbon, what's going to be our product? And the product here, the little dotted lines just are implying a absorption phenomenon. So I'm just showing a little dotted line. Sometimes in the book, it shows fuzziness with electrons, just trying to show that the hydrogen is absorbed to the surface. Okay, if we add only one equivalent of hydrogen, what our product actually is this and this, right? The reason for this is that the alkene reacts faster than the alkyne. So with palladium, platinum, and most nickels, right, what we do is we end up with, this is the faster, this is slower. So if we try to only add one equivalent, we don't end up with the alkene. What we end up with was just, you know, 50% of the reduced product and then 50% of the starting material. So theoretically, we should be able to do this, right? We should be able to stop at the alkene, but the problem doing it here is that by adding one equivalent, we just make a reaction bad, right? We don't do what we want to do. So what we need to do is reverse this. We need to have the alkyne reactive and the alkene not reactive, right? So what we need to do is figure out a way to make a catalyst that will react with an alkyne and not react with an alkene, okay? So what we need is a poison catalyst. I think I misspelled that. Poison catalyst. I can't spell. Poison catalyst. Poison catalyst. Anyway, so it's I'm losing it. I can't spell it. Right. So Lindlar's catalyst. Can do this, right? And what happens is it gives a cis alkene. To make Lindlar's catalyst, what we do is we take palladium and we absorb it on calcium carbonate with lead oxide. So there are several different catalysts. Thank you. There are several different catalysts. Lindlar's catalyst, and many times in these, organic undergraduate organic classes, they just say Lindlar's catalyst. But the important parts, what you'll notice is if you're ever taking a standardized exam and you say lead and one of the platinum, palladium, or nickel, and usually some type of calcium salt, it's going to be a poison catalyst. These are the things you see is the lead with the palladium and then some type of calcium salt. So you could have calcium sulfate with lead sulfate. That's another catalyst. It's a version of Lindlar's catalyst. And so, but what these do is that now it's reactive only for the alkene. The alkyne. Only reactive for the alkyne. It's not reactive for the alkene. Notice that both hydrogens come to the same side. That's because we're adding the hydrogens, right? Still on a metal surface. So we still are adding the metal surface like we saw with the alkenes, right? So that means that when we use the poison catalyst, we're always going to get cis. The other catalyst you're going to see is a nickel boron catalyst. Because lead is toxic and they were trying to make some pharmaceuticals, they came up with other ways to do this. So nickel boron, and sometimes known as nickel NB2, I think is what they call it. And I can't remember, so I won't add it right now. I'll show it to you later. We get the same thing, right? It's still kind of a metal surface, but this is a poison catalyst, right? Yes, it's cis because the addition has the same side. So you could think about this as a syn addition. P2, thank you. P2 catalyst. Y'all are helping me out great today. Okay, so we have a way to take an alkyne all the way to an alkane. We have a way to take an alkyne to a cis alkene. So what's left is we need a way to take a alkyne to a trans alkene, and that's where we have the dissolving metal. And now on this one, notice we're using sodium in NH3. Okay. This is a confusion alert. Right? Students will get sodium amide, NaNH2, confused with sodium and ammonia, right? Especially when sometimes you'll see sodium amide in ammonia, right? So these are not the same. Watch for this. This is a big mistake students make often. You just get those confused. This is sodium metal in ammonia. And what the sodium metal in ammonia does is it gives you the trans alkene. Now, this is done because this is a radical reduction, which it means is we're going to, most of our metal, our sodium and lithium reductions are going to be radical, meaning one electron reduction. So the way this works, and I'm going to make a simplified alkyne here, is remember that sodium has one electron. So the sodium has that one electron. It gives up the electrons. We end up with this species where we got a radical. In the corner. At this point here, right, you notice that we have the radical and the lone pair. We have these electrons. So these electrons can move around until they get to the more stable structure. Right. And so that's why we can end up with our product this way. So because the intermediate has the electrons here, these electrons will go to the point that's most stable, and trans is the most stable. So it's this kind of intermediate where we have our electrons and our radical there that we form the more stable, and that ends up giving us the trans product. Okay. All right. So let's pick the reagents now that we've looked at our three. So I'm going to put three different alkyne reductions here. You tell me what reagent we should use to get the right product. Okay, let's look and see. So whenever you see this type of reduction, I always think it's good to go ahead and, look at your functional groups. And this is a cis alkyne. Right here, we got an alkyne going to, alkene going to a trans. And again, lots of us tend to focus on our abilities verbally, right? That's how we got as far as we did. So alkynes. So alkynes to cis alkenes. Okay, for that one, we're going to use a poison catalyst. So we could use hydrogen and Lindlar's catalyst. Or you might have put hydrogen and the P2 catalyst. Thank you for giving me the abbreviation for the P2, the nickel 2 boron. Okay, the second one, alkyne to trans. Here we're going to do the dissolved metal. Okay, don't get thrown off, right? If you see lithium in ammonia, that also works. And then sodium slightly cheaper than lithium, but especially now since lithium is used for batteries. And then alkynes and alkanes, here we can just use our standard palladium on carbon, right? So we can use just the standard. So. For the I won't ask you what the Lindlar's catalyst reagents are, but you should be able to recognize that it is a Lindlar's catalyst, right? And so that's, if you see a combination of lead, some type of salt, and then, so if you see a combination of some palladium, lead, and then some type of salt, you should recognize that as a poison catalyst. Same thing here. If you see nickel with boron, you should recognize that as I'm not going to ask you what P2 catalyst is. I've seen it on exams. I've seen it in test banks. But I think what you should be able to do is recognize this. So if you see this reagent, recognize that this is Lindlar's catalyst. Okay. All right. And again, with Lindlar's catalyst, you'll see different variations of it. It's a lead, it's a palladium or platinum with a lead with some type of salt. Usually it's calcium salt. Okay. All right. As I said, we're kind of going fast through this, and we're actually going to do 2 more reactions. And that's because so far, everything is very, very similar to our alkenes. So these are additions to alkynes. They're very similar to our alkenes. There's just slight variations. As you see here, there's a variation because now I could stop at the alkene. I don't have to go all the way to the alkane. And so again, this is very similar to alkenes. In fact, if you look over these, it's good to look and see what the differences are with your other reactions. Okay, so like with alkenes, let's go with hydrohalogenation. Okay. If we add one equivalent, we can add one equivalent of an alkyl halide, hydrohalogen, right? HX. We can add one equivalent. You'll notice that there's one equivalent is written, one EQ. Sometimes you'll see it written out as one equivalent. In that case, what we end up with, we only add one hydrogen and one X. And that's going to be the more substituted side. So we can think about this as kind of a Marco style. Now, we are not ending up with a same carbocation we saw with Markovnikovs, right? This is an sp2, but we end up with a more stable species, right? So that's, you can say that's Markovnikov style. If we had added, an excess or two equivalents, You know, if they have something like this, or sometimes you'll see HX and XS, right, as equivalent, XS. Right, then what we'll get is we'll get double addition. Questions about those? Not going over the mechanisms here. The interesting thing about the second mechanism is that whenever you add two equivalents here, you actually end up with this weird intermediate where you're involving three of these. And it turns out the rate determining step here is third order. So interesting part of this. When the book doesn't go into it, I'm not going to pick on it. The big part here is to realize with one equivalent, you can stop. That's not what you saw with the reductions. Two of equivalents. Right, and two equivalents just adds, I'm going to add twice as much of the HX than my substrate. So I'm going to add one equivalent of the substrate and two equivalents of my hydrogen halide, or I add 1 to 1. So if you think about cooking, right, I'm just doubling up. So I'm going to add twice as much of the reagent. So one equivalent of the reagent or two equivalents of the reagent. And like before, right, we have a radical process that can give us the opposite. So we can have the radical addition. And again, 1 EQ, 1 equivalent will get us this. If we add a second equivalent, actually, okay. The problem here is that if we add a second equivalent, there's some oddity about having the bromine on there. So let's take a look. If we add the bromine on there, right, and let's say that I just added HBr. Now, what I want to do with the HBr is I actually want to get the most stable carbocation. So if we look at our two possible carbocations, right, this one or that one. So if we added the hydrogen here to get the secondary carbocation, or if we add the hydrogen here to get this primary carbocation, it actually turns out that this has a resonance contributor. So what that means is that this is the more stable. So this carbocation, which is secondary and we think was more stable, is not actually formed. It's the one that's next to the bromine. So then as we look at this, then it's actually this, wherever the bromine is attached, that's where this second bromine is going to come in and attack. What that means for this one is that if we try to use two equivalents, we're actually going to get a vicinal, one bromine on one side, one bromine on the other side. So when you see this radical addition, you often only see it with one equivalent, and sometimes they won't show it with two equivalents, because there's an oddity. Once you add that bromine, it actually turns out that the primary carbocation, because of this resonance, right, is the more stable. So once the bromine adds, right, then all of a sudden, wherever that bromine adds, that's where the more stable carbocation is going to be, which means that if I just added normal HBr, it's going to go to the bromine. If I had tried to do the radical one, I would have ended up with it in the wrong place. Okay. So when you see the radical additions to alkynes, you almost always see it with just one equivalent. And in fact, the book sometimes will just not list equivalents. It'll just say HBr and hydrogen peroxide. Okay. All right. We've got a couple of minutes, so let's do a couple of try this. Put a few reagents here. You let me know if you can, you tell me the products.
Dr. Morgan, that first one, it's a bromide with two equivalents or one equivalent or
Excess. So you got all you want. Okay, we're running short on time, so let's go ahead and look. So in excess, right, what we're going to get is the full tetrabromination of the dibromide here. And I'm not sure if I remember to show you that one. So if you got that one right, bully, you did great. Okay. Sorry, I watched Night at the Museum with my kids this weekend. So if we look at the second one, right here, we're going to form the more stable, and that's going to be the internal, right? So we don't need the second step with the water. So we end up with the alkyne. So we get double dehydrohalogenation, right? We end up with two eliminations. And then this last one, we're going to end up with a dissolving metal, which is going to give us the trans, right? All right, questions about either of these?